Hello and welcome to this talk about synthetic undecidability and incompleteness of first-order axiom systems in Coq, which is joint work with Marc Hermes. I want to start with this question: why revisit undecidability and incompleteness? And part of the answer can be given in two screenshots. If you look at incompleteness in logic on Google Scholar and restrict to the last 10 years, you still see more than 24,000 new publications. And instead, if you go to YouTube and enter incompleteness, you might, for example, run over this video, which has been published just a month ago and already has more than 7 million views. So one can say that undecidability and incompleteness are discussed by a broad audience in and outside of science. And then relevant to this conference is that they are also a prominent benchmark for interactive theorem proving, and they are known to be somewhat hard to mechanize. And since they are hard to mechanize, they are also a good case study for a particular approach to mechanizing these results that has been used in previous projects. And talking of previous projects, so if we look at undecidability in first-order logic, there's a couple of decision problems one can consider. For example, provability or validity, satisfiability by some model or satisfiability by a finite model. And while all of them are known to be undecidable from very classical papers, only recently Coq Mechanisations of these results have been given at ITP'21 and at ITP' 2020. And now for this class of problems, in this talk we will talk about a related class of problems, namely the decision problems relativized to an axiomatization. So now we can ask whether a given formula is derivable or semantically entailed by this formula, by this axiomatization. And then we call axiomatizations undecidable if these problems are undecidable. And then the observations we can make is first, of course, this relativized class of problems is connected to the general decision problems. So if an axiomatization which is finite is shown undecidable, then by this we also get undecidability of the general case. And then the problem is of course non-trivial. So of course many axiomatizations are known to be decidable. There's the technique of quantifier elimination with which you can prove a lot of axiomatizations decidable. But on the other hand, of course, if axiomatizations are strong enough to express undecidable problems like Peano Arithmetic or ZFZ theory, then those axiomatizations can be shown undecidable in turn. And while many mechanizations of decidable axiomatizations are around, there are no mechanizations of the undecidability of axiomatizations, at least like Peano Arithmetic or ZF. Okay. Then from undecidability, there are these links to other properties of axiomatizations, most interestingly to consistency and incompleteness. And those links are established by the contraposition of two facts. So the first fact is an axiomatization that is inconsistent, so derives falsity, must be decidable. And that's trivial because inconsistent axiomatizations prove every theorem, so they have a trivial decider. But this also means now, if we look at the contraposition, that mechanizing undecidability of such an axiomatization is at least as hard as mechanizing the consistency. And mechanizing consistency may, depending on the axiomatization, be not straightforward or even exceed the consistency strength of the theorem prover you're working with. In our strategy, this doesn't show up as a byproduct, but it's actually integral to the strategy because we work with standard models anyways that show consistency on the fly. And now the second statement is the link to incompleteness. And positively, this means that negation complete axiomatizations, so axiomatizations that for any sentence phi either derive phi or refute phi, that they are always decidable. And this is the link that gives you from a proof of undecidability a proof of incompleteness. And this also means that proving undecidability is at least as hard as mechanizing incompleteness. And here, of course, a little disclaimer. Of course, from this observation, you get incompleteness in the non-informative proof that doesn't construct you an actual witness for incompleteness. All right. So I've mentioned that there's not many mechanizations of undecidable axiomatizations, but incompleteness is a very well-known benchmark for theorem proving. And the first to actually finish a complete proof of Gödel's first incompleteness theorem was Shankar in 1986 using the Boyer-Moore theorem prover. And then, I'm of course not giving an exhaustive list, there was Russell O'Connor who proved the same theorem in Coq using constructive means. And Paulson was then the first to mechanize also the second incompleteness theorem using Isabelle Holl. And then the last thing to mention on this very broad list is that Popescu and Treitel also discussed abstract preconditions for these theorems to hold. So they give a more abstract treatment of these results. And then what they have in common is that they all follow Gödel's original proof. So they mechanize the direct, or they could directly construct Gödel sentences, while none of them use the treatment via undecidability, which, depending on how you do it, is indeed a much quicker way to get these results. And we will see this in the rest of the talk. So the plan is that we first have a look at the framework, where we develop synthetic undecidability and incompleteness. And then we have a look at the case studies, focused on theories for arithmetic and set theory. And then I conclude with some remarks on the Coq mechanization and on future directions. Okay, so we start with the framework. First, synthetic undecidability, as it has been already developed in 2019 in the CPP paper. And this approach is based on the fact that in constructive type theory, and actually most other constructive foundations of mathematics, every function you are able to write down is computable by definition. And the advantage for this is that a lot of positive notions from computability theory can be defined in a very simple way. For instance, if we look at a problem P over a domain X, we can say that P is decidable if there is a function from X to the Booleans that coincides with the problem P. And it's enumerable if there is a surjection from the nature numbers into X that captures P, and it's reducible to another problem on a domain Y if there's a function from X to Y preserving the predicates in both directions. And the clue is that all of these functions, F, G, and H, can be defined in a meta theory, and there is no need to also encode them in, for example, Turing machines to show that they are computable. And for mechanization, that makes a huge difference. And now, when we turn to negative notions, and we want to, for example, define what undecidability is, then one first attempt could be to say it's the negation. So decidability of P implies falsity. And now here it depends on how your meta theory looks like. Constructive meta theories are sometimes, or at least Coq's type theory is agnostic to the interpretation of the computability of functions. And so one thing to add, which works in for example, Coq's type theory without adding axioms, is to say that the decidability of P implies the decidability of, for example, a halting problem on Turing machines or another model, which is known to be undecidable. And then one gets an interface on how to establish more undecidability, and that's the standard way using reduction. So if I can mechanize positively a reduction from the halting problem to problem P, then undecidability transports along this reduction. Okay, that's the framework for synthetic undecidability. Now we have a look at first order logic, which has also been used in a previous project. And the general approach is that we represent the syntax over a signature sigma with function and predicate symbols with inductive types for terms and formulas. Terms have variables function application, formulas have falsity predicate application, all binary connectives, all quantifiers. The semantics is given by interpreting the syntax in type theoretic models, so models consisting of a domain type D and respective function interpretations and relation interpretations, and then by mapping all the connectives and quantifiers to the counterparts in the meta theory, which without axioms first behave constructively. And then the provability predicate can be characterized by inductive predicates of intuitionistic and classical flavor. And then, since the meta theory is first constructive, this means that only the intuitionistic deduction system can be shown sound constructively, and the soundness of the classical deduction system requires excluded middle, and this will play a role later. So on this setup, we can define what an axiomatization is, and it's just a predicate on formulas which is enumerable, so we have enough computational cross on it. And then we can define the decision problems, for example, the semantic. decision problem talking about the formulas that are semantically entailed by A, and also we have the deductive decision problems. All right, now we have enough developed so we can have a look at the true facts from the beginning again. And we can now look at the proofs as well. So first, the link between undecidability and consistency can be stated if a predicate P reduces to an axiomatization and P is non-trivial, then the axiomatization must be consistent. And now formal proof can be given by first assuming F to be the reduction. Then on the point X, which is not in P, we can have a look at its image under F, and we know because F is a reduction that this formula f of x is not derivable. But if there is an underivable formula, then by the explosion rule, falsity cannot be derived. And this is already the full proof of this connection. And now turning to the a bit more interesting connection, the link to incompleteness, is that if a predicate reduces to an axiomatization and A, this axiomatization is complete and consistent, then P is decidable. So in particular, if we plug in the halting problem for P, we get that if we verify a reduction, then the completeness of this axiomatization would entail the decidability of the halting problem. So it's almost incompleteness. And the proof looks as follows. We can just use Post's theorem to show that A is decidable if it is complete and consistent, because for this, we just have to show that it is enumerable, and enumerability is immediate by enumerability of the deduction predicates. And then we have to also enumerate the complement, but for complete and consistent theories, unprovability is the same as refutability, which is enumerable, so this works. And then since we are in a constructive setting, Post's theorem actually has a side condition. And for instance, the side condition can be satisfied by showing that the axiomatization is logically decidable. So we have a logical decision whether A derives phi or does not derive phi. And this we get also from completeness and consistency. And then we have A shown decidable. And from this, we can just transport back to decidability of P. OK, so that's the links for the general treatment. And now we end the part on the framework with an overview how we then tackle the undecidability reductions for specific axiomatizations. So first we pick a suitable undecidable seed problem, suitable meaning that it's easy to encode it in the language of A by giving a nice reduction function and being able to write this reduction function without developing a lot of theory inside of A. Then in fact, it's in most cases possible to isolate a very weak fragment of the axiomatization that suffices to verify the reduction. And doing this is good because then your results are stronger, because then it generalizes to more axiommatizations. And also, in fact, the mechanization is simpler. And then the verification is done semantically by showing that solvable or that actual solutions of the problem are valid in every model. And for the converse, we show that if a model thinks that there is a solution, then this is an actual solution, at least if M is well behaved enough. So it's standard in the sense that, for example, only standard numbers are contained in this model, or standard solutions. That's the part that is necessary here. Then one, of course, has to construct such a standard model to be able to use the previous point. And then we are done with the semantic verification. And the deductive verification can be done by repeating the fourth step, so proving that P of x always implies that from A we can derive f of x, which then, depending if we have a completeness theorem around, if the logic is strong enough to show completeness, then this of course follows directly. If not, it's actually possible to do it by hand. And then by general means, we can say that if all these ingredients are given as above, then for every axiomatization extending the one we verified the results for, we obtain a reduction into the validity problem and into the intuitionistic provability problem. And if we have soundness, so for example, with excluded middle, then we also get the reduction verified into the constructive, into the classical provability predicate. Okay, so now with this preparation, we can have a quick look at the case studies where we just follow the recipe. So for Peano Arithmetic, formalized over the usual signature with zero, successor, addition, multiplication, and equality, we pick a seed problem which is easy to encode, and that should be an arithmetic problem. For example, the solvability of Diophantine equations, Hilbert's 10th problem, which has been mechanized to be undecidable before. The reduction function is indeed really straightforward because a polynomial equation can be directly expressed in Peano Arithmetic, and we just have to add enough existential quantifiers to bind all the variables appearing. As a core axiomatization, it suffices to take the 4 equations characterizing addition and multiplication, nothing more. And then the verification is straightforward, just using that every natural number has, of course, a straightforward representation into Peano Arithmetic, and then all the results necessary follow. And as a standard model, we pick the standard model that we can define in Coq's type theory, so the type of natural numbers with usual addition and multiplication. And then by the general theorem from before, we obtain that this core axiomatization and all its extensions, like Robinson arithmetic or full Peano arithmetic, are all undecidable and incomplete in the sense discussed before. And even without them, we get these results for the respective fragments of intuitionistic flavor, so for the fragments of Heiting arithmetic. Okay, the second case study is about set theory. So here we first pick the easy signature, giving us a lot of function symbols for all the set operations. And that's easy because then we can really easily write down a lot of constructions. And in fact, this language is so strong that we can, of course, just define any problem in it. And the one we happen to choose is the post-correspondence problem. There's a little reason for it, but it's actually not that important. And the PCP has been shown undecidable in a mechanized way before as well. And then the reduction function can be given by just encoding enough of the ingredients needed to state PCP and encode a bit of recursion. I have a backup slide on this if you're interested. As a core axiomatization, we also don't need much. We just need the extensionality axiom plus the characterizations of these operations. And then the verification is done by just developing enough basic set theory such that the recursion theorem can at least be inlined, and then verifying everything we need. I also have a backup slide on this if you're interested. And the standard models that we need are the models that interpret the infinite set omega as the natural numbers. And for full set F, this indeed needs some assumptions. And there I have a third backup slide. So with all these in place, we can conclude that the core axiomatization and all the extensions that are satisfied by standard models, like set or set F, are undecidable and incomplete. And again, even without them, we get these results for intuitionistic variants of set theory. Okay, there's one more thing one can do. So as I said, this signature eases your life in writing down the actual reduction function, but the most minimal approach to set theory is of course to just have the membership signature. And I don't want to talk a lot about what to do in this signature, but of course you can write down the axioms, and you can also verify the reduction from before. In fact, it's, I guess, unfeasible to do it directly. So instead we verify the translation from the previous signature, which is not too complicated. I can't go into detail now, but I'm just interested in this theorem saying that, of course, this axiomatization is already undecidable as well. And then most importantly, the corollary that by transporting this finite axiomatization back, we also get that first order logic with a single binary relation symbol is undecidable. And this is an improvement over the development we discussed before at CPP'19, because there we used a custom signature, not the minimal signature. Okay, and with this I want to conclude. First, a few notes on the Coq Mechanization. So it is mostly axiom-free. We only use excluded middle very locally, and the axioms we need for the models of ZF. The full mechanization is a synthesis of previous developments we have used for other projects. And on top of those, we add a bit more than 5,000 lines of new code, where we remarkably, we just need 700 lines for the reduction from H10 to PA. A bit more, so this includes the undecidability and incompleteness result. A bit harder is the verification of ZF, in particular the deductive part. And then, of course, more than half of the work was on the signature transformation that I just showed briefly on the last slide. And since this was really hard work, this inspired tooling. So in fact, if you're interested, you can have a look at our talk at the Coq workshop on Friday, where we discuss a few of those tools. And most of, or all of the results here are included in the Coq library of undecidability proofs, which has already been discussed at last year's Coq Lab. Okay, some future directions. I can't explain all of those, but for strengthening and generalization, we hope that we can get rid of the use of lem, which should actually be possible. And we can also strengthen in the sense that if we extract all our reduction functions to a computational model using tools, we get actual undecidability and incompleteness and not just implications to the decidability of the halting problem. And there's also some more ideas. All right, and with this I want to wrap up, and probably the bottom line of this talk is that synthetic approaches ease the mechanization of undecidability proofs, which we already have used in a lot of projects related to the library of undecidability proofs. And then by using this computational way from undecidability and incompleteness, this also shows that synthetic approach eases the mechanization of incompleteness by a lot. And the synthetic approach is available in most constructive foundations. And you can have a look at our paper and on the development if you click on this link to the project page. And I'm very grateful to answer any of your questions, and thank you for your attention.